Welcome to the webinar for our newest RFI, AirTight and EcoFriendly. I'm Shivani Ludwig, manager of this RFI, and on this video, I'm going to describe the request for invention, the solutions we are seeking, and what is in or out of scope, along with some additional background material for this topic. If you have any questions about the RFI or would like to submit a very brief summary of your idea for feedback, you can reach me at my email address, which is found on the screen, sludwig@xinova.com. You can also ask your questions about the RFI on our RFI opportunity page. On the right-hand side, there's a bar where you can post your question and receive answers from Xinova staff. I'd like to point out that this RFI closes on February 3rd, 2020, and so I encourage you to submit your ideas before that date so that we can get back to you with some feedback to make sure we're ready to share the top solutions with our client afterwards. Xinova's partner in this RFI is Stora Enso, a manufacturer of pulp, paper, and other forest products headquartered in Helsinki, Finland. Their products include paperboard for packaging of dry and liquid products, corrugated fiberboard, pulp, construction materials and fuels produced using wood, as well as paper for commercial printing and office use. In this RFI, we're focusing on paperboard. Stora's paperboard production capacity is 4.7 million tons per year. So, in thinking about this RFI and solutions, it's important to keep in mind this volume and scale. The supply chain for the paperboard industry and for Stora begins with the conversion of raw materials, that's wood, into chips, pulp, and ultimately the paperboard. This is then coated with various layers by Stora Enso manufacturers. At this point, Stora's paperboard products are sent to converters, where they're converted into packaging for specific applications, such as dry food, liquids, and more. These may be sent to filling machines, where brand manufacturers assemble the final package for their food or beverage product. These are then what lines shelves at the grocery store for consumer purchase. In this RFI, we're focusing on the coating aspect, but solutions may also indirectly impact the paperboard manufacturing stage as well. We'll next take a little deeper look at this process to help understand the paperboard product which you are being asked to improve. Paperboard has several layers of pulp. These pulps are mixed, diluted, often with chemical additives added for various properties such as strength, tensile stiffness, smoothness, brightness control, and more. The top ply is the most outward facing, and so it must be smooth enough to allow for printability and a smooth appearance. The middle plies can consist of several layers depending on the application for this paperboard and include both bleached and unbleached chemithermomechanical pulp, or CTMP. The reverse ply is the internalmost layer. The first pulp layer is formed on what's called a forge veneer. You can see a schematic on the screen. This process includes pressing the wet pulp using many rollers, a dryer section where 69 cylinders with increasing temperature efficiently dry the pulp, and the water is drained upwards by vacuum. This is followed by a calendar section where 2 or more rolls make the paper surface extra smooth and glossy. Other pulp layers are then formed on top in secondary formers called simformers. After the paperboard is made, dried, and rolled, the next step is to add coatings as appropriate. This includes coatings on the top ply that further reduce roughness, along with printing, as well as coatings on the reverse ply side. These latter coatings include polyethylene, which provides water resistance and serves as an adhesive layer for the aluminum layer, which acts as a barrier against gas diffusion, water vapor, odor, and light. This figure is one example of a grade of paperboard. You can see the thickness of the middle plies as well as the aluminum foil layer in white and the many uses of polyethylene layers. Stora makes different grades or weights of paperboard with different thicknesses. The total range of thickness is approximately 100 to 350 grams per meter squared. There are also many coating processes that are commonly used in this industry. In the figure on the right, you can see the process of extrusion, where melted plastic beads are extruded offline, coated directly onto the paperboard. Coatings can also be added through lamination, where a thin layer of molten plastic is added to the board, or through dispersion, where a water-based polymer solution is dispersed onto the paperboard inline at a much faster speed. In this RFI, we're focusing on aseptic packaging. If we look at the various types of packaging for food across shelf life and barrier complexity, you'll see that barrier complexity must increase to enable a longer shelf life. In the first category, you have packaging used in food service, which often needs to last minutes or at most hours. Fresh food, on the other hand, must last weeks, and so has even more complexity in its barrier. And finally, food contained in aseptic packaging must have a shelf life of at least 6 months, or often up to 3 years if unopened. This means that the food and beverage contained within must be fully protected from external moisture, oxygen, odor, and light. So this is the focus of this RFI. The current design for aseptic packaging for liquids includes the following layers as shown in this figure. You'll notice that there are many polyethylene layers in this package, each serving a different purpose. The first innermost layer of polyethylene seals in the liquid. The next layer serves as a tie layer, or an adhesive layer that ties to the aluminum foil layer. Aluminum is the current industry standard for a gas barrier. It's able to protect against oxygen diffusion, flavor and odor diffusion, as well as light. The next layer is, again, a polyethylene tie layer that binds the aluminum to layer 5, which is the paperboard. This, of course, provides strength and stability. Lastly, there is a final layer of polyethylene that protects against outside moisture. In this RFI, Xinova and Stora Enso are seeking to replace the aluminum layer with a more sustainable, but equally or more effective gas barrier material. Ideally, this new material would itself be adhesive, so that would eliminate the need for the tie layers 2 and 4. Aluminum is problematic in aseptic packaging because it has to be separated from the paperboard in order to recycle the remaining package. This is currently done in some places where the aluminum can then be reused to manufacture, for example, roof shingles. However, the overall package can't be reused for packaging material without the separation, and the aluminum itself isn't recyclable as a packaging gas barrier. So in this RFI, the goal is to identify a gas barrier that allows the full package to be fully recyclable into new paper or paperboard with less than 20% rejection, ideally less than 5%, and without needing to remove the gas barrier layer. Even more ideal would be a package that is repulpable, meaning the pulp fibers can be recycled for reuse in any application similar to virgin pulp fibers. So this area has been a hot one for innovation, with many working to identify sustainable solutions for years. Examples of solutions that have been explored include cellulose, including multifibular cellulose, polyvinyl alcohol, ethylene vinyl alcohol, polyamides, alginate proteins, polysaccharides, and more. However, to date, these haven't been able to provide commercially viable solutions for several reasons. One, the layer may not have sufficient plasticity, meaning it's too rigid for this application. So as the material is folded into the final package shape, the material and therefore the gas barrier within will weaken along the creases and folds. Some of these solutions have been sensitive to high moisture. The paperboard manufacturing process results in an especially high moisture environment, so that's an important aspect to consider. These solutions may not be compatible with current methods for application, such as industrial coaters being used. So that makes it more challenging to efficiently implement solutions when it's critical to be able to implement these at the high scale needed. Or finally, it can just be too expensive to implement these solutions, requiring complicated combinations of layers and barriers to get the same level of barrier strength that you can get currently with aluminum and polyethylene. So, Xinova and Stora Enso are seeking new, sustainable materials for a gas barrier for aseptic packaging. In this RFI, we have a pretty hefty number of key requirements, and so it's especially important to pay attention to these detailed requirements. On the slide, I'm sharing the requirements, but there are many more details in the RFI document itself. The first one, of course, is to have a strong gas barrier under varying climates, and the RFI has more details on the specific gas barrier strengths under different humidity levels. The key thing about this requirement is that the barrier strength is often variable with the amount of barrier material being used, and so there's a trade-off there that should be acknowledged. So you may propose a material that provides a strong barrier, but if a significant amount needs to be used, it may not be compatible, it may not be commercially viable. It's important for the solution to be food safe, so there's no leaching or any effect on odor, taste of the beverage. It should also not be toxic to microbes, but also not promote microbial growth. Again, the material should be flexible, so it doesn't crack when the paperboard is folded. The barrier material should be recyclable, and this is where it would differ from the current standard of aluminum. Since this is being used in aseptic packaging, it should be functional over a shelf life of at least 6 months, preferably 3 years. And finally, it should adhere to the water-resistant layer, or if it has water barrier properties, then we are eliminating the need for a water-resistant layer, which is actually an added advantage. There are also key requirements for commercial feasibility. So it's important to consider cost. Stora Enso has noted that the cost increase, they can tolerate a cost increase of 20 to 100% per meter squared of barrier initially. And to help with that, they noted that the aluminum layer currently used can be between 0.6 and 6 microns. The material should allow for scalability, and it should be available to enable pilot production speed in 3 to 4 years. So a key thing to note in your solution when describing a new material is how that material may be obtained or developed in a reasonable time. And lastly, it should be compatible with conventional coating processes. There are a few other aspects that would be nice to have and could help your solution stand out when considering others too. It helps if the barrier can also provide if the material can also provide a barrier against water or against light. But please note that that is not the key focus of this RFI. The key focus of this RFI is to provide a gas barrier. It's also an advantage if the material can bind directly to the paperboard, which means that you no longer need those adhesive layers or those tie layers. It's also ideal to lower the carbon footprint. As mentioned, the circular economy, it's good to lower the contribution, the carbon contribution from that material. Should be GMO-free. It should also not use raw materials that are sourced from food crops, meaning it wouldn't be food competing. The preparation time for a solution of this material should be less than 12 hours and ideally less than an hour. And finally, for dispersion coatings, there's a couple of things to note. It should be water-based and film forming below 100 degrees Celsius. And the brick field viscosity should be 500 to 2000 centipoise at 40 degrees Celsius. Finally, there are a few things that are considered out of scope. Application conditions below 0 degrees Celsius would be out of scope. We're also excluding a few different material options. These include commercial starch-based barrier coatings, micro and nanofibrillar cellulose films and coatings, chitosan-based films and coatings, as well as commercial barriers based on extruded PLA, PBS, PHAs, PVOH or EVO as well. If there are any questions about some of these out-of-scope aspects, please reach out. We can share a little bit about why these are out of scope. A key thing about this and any other RFI is to identify something that is patentable and new. And so a reason why something may be out of scope is that it is being currently explored or has been explored to by so many additional parties, and Stora Enso is looking for something that's particularly new. Finally, a key aspect of this RFI is a new solution report template. This template is hopefully much easier to work with. Our goal was to clarify the instructions, keep it a bit more concise. The overall goal of this template is to help you help us understand your solution. We want to know what is novel and how does it meet the RFI requirements. So each of the sections provides a very specific thing that we need, so it's really important to fill out all of the sections and to be thorough in all of them. The one exception is the summary, which should be very clear and it should be brief, less than 150 words. This is critical because this is often the only thing read by some parties, and it's a critical part of our literature knockout search when looking at what is new or not new. So the summary, though it's brief, should very concretely describe the key aspect of your invention. This solution report template is available on the RFI opportunity page. If you go to the page, it's available for download from there, or if you're not able to find it or the download does not work, please reach out to me by email. We're really excited to see our solutions for this RFI. As a reminder, it closes February 3rd, 2020. So I encourage you to ask questions, reach out with your ideas, and when you're ready, submit your final solutions. Thank you.